Okay, shall we start? Um, so again, as usual, if you have a question, just send me a message via widget. And if you encounter a network problem, just let me know. I'm not sure if I can do something better, something to network, but I'll try. Okay. So the last time we talked about running coupling constant, common Weinberg potential, we start talking about the gauge theory, especially going to nonlinear gauge theory. But I forgot to mention one thing. Why this gamma is called anomalous dimension. That I forget to explain last time. So, and one student asked me that the why the beta function of phi. So one student asked me that the phi theory in dimension d. So beta function can be written d minus 4 lambda plus 3 lambda square 16 pi square. And how to get this one by dimensional analysis? So I just told you this is dimensional analysis. But one student asked me how to get this one. So to get this one, so you just know that the action has the kinetic term for action in d dimension is something like a so the mass dimension phi from here can easily see that the d minus dimension minus 2 coming from derivative d minus 2, and there are two of them, so divided by 2. So the mass dimension phi is d minus 2 over 2. Therefore, phi to the 4 has 2d minus 4. Okay. And this part, as I mentioned in the previous lecture, so it should be operator has dimension. If operator has a dimension di, so di in this case 2d minus 4, here di minus d, which is 2d minus 4 minus d is equal to d minus 4. That's how we get the here from dimensional analysis. And from there, so we just found, I think we maybe, so this is the beta of lambda. From here, you get lambda. And then here, so first, when these less than 4, so here it's negative. So it's leading, if lambda is very small, the first time leading term is the dominant. But if lambda goes increase, or absolute value of lambda increase, so the second term becomes dominant, so that the curve is bended and hits to 0. So this be beta of lambda star, and here is equal to 0, and here it's called Wilson-Fisher point. Fisher point. Fisher point. And now people often call IR fixed point. So that's how we obtain the Wilson-Fisher point from dimensional analysis. And then I forgot to mention one thing. So the column semantic equation, we just write down the new portion here plus beta partial lambda plus gamma essentially of g is equal to 0. So this is the essential form of the column semantic equation, and then I call lambda is anomalous dimension. But I didn't explain why this gamma is called anomalous dimension. I promised to explain why it's called anomalous dimension, but I didn't explain last time. I forgot to tell you, sorry. So I will explain before I'm going to the nonlinear gauge theory. Yeah. So let's consider the scalar theory, some scalar theory. Scalar theory. And the two-point function in two-point function in scalar theory. So G2, and in momentum space, G2 of P can be written as follows. So so we assume it's the massless scalar theory. Sorry, massless scalar theory. Then the property that takes the following form. The most general form of property that takes the following form, mu square. Okay. This is the most natural form one can consider, because this is dimensionless, and the two-point function should have the mass dimension has to have, let's see, mass dimension is minus 2. So therefore, this part is will give you mass dimension minus 2, and here if you take the ratio, it's dimensionless. So you can just have some arbitrary function of the let's use small g of the ratio between the momenta. So that you just consider property of momentum p, and mu square is the one you measure, the scalar you measure. So we can just rewrite in momentum space this equation by instead of using a mu derivative, one can use p derivative. So just rewrite the Collins. So this is Collins semantic equation. In terms of momentum basis. So instead of mu derivative, I will write down p derivative, which you can just easily see from here. So mu derivative can be translated p derivative, but you have to consider cost of the factor 1 over p squared. So you just swap the and plus 2. So this plus 2 really come from this derivative. So if you add this p derivative on here, you get 2 minus 2, so that should cancel with this one. Okay? And then so you have a let's say two-point function will give you this 2, and z to p. I hope the network today is okay. Looks to me okay. So that's what you get. And then if beta and gamma is 0, you just from here you just get the ordinary solution. You get the G2 of P is just I over P squared. So this should give you 1. Okay. It turns out that in fact, the Coleman noticed that Sidney Coleman, who is a legendary quantum theorist, I told you once, right? So there's a advanced look of aspects of symmetry, which after this course you can just stop reading. But anyway, Coleman noticed that this rewriting of Collins semantic equation looked like it's the same form as the so-called some differential equation v of x. So this was famously studied in the So these in the bacteria equation is called Tx equals 0. So where the analogy really come from as follows. So lambda, so log, if you just compare between them, so the analogy is log p over mu is the same as t. If you take the log, of this one, and then just the up to -2 factor, you can just compare with t. And then lambda corresponds to x. So this lambda derivative corresponds to x derivative. And of course, you can just compare this one with here. So 2 gamma lambda minus 2 is rho x. Okay. And then of course the solution, 2-point function corresponds to the function, so d. Okay. And it's, so the solution of this equation known as follows. So the solution of this equation is known as follows. So of course this differential equation, you have to put some initial value. But after putting initial value, what you get is some initial condition which determine x and exponential of 0 to t dt prime. So it's just this differential equation has this integral solution x bar t prime x. Yeah. So this is the solution one can have for, so it is known that so this has the solution like this. Yeah, so where of course, the initial satisfy the equation that the ddt prime x bar, t prime x is given by minus, so b is kind of like considered as the velocity, and then you just put the initial condition as follows, is some value x. So given the initial condition and speed b, you get the solution like this. So therefore, so using an analogy of this one can just consider construct the solution for column semantic equation. As follows. So G2 of P and the lambda is some function. Let's go G hat lambda mod of P lambda such that exponential. You just use the analogy given here. Analogy given here. Oh, did I write the analogy? Oh, sorry. So of course, minus beta of lambda is given by b of x. So by using analogy, so what you will get is p prime is equal to mu, and the p prime is equal to p, and there is a negative sign, so minus sign, such that d log p over mu. So since this t integral can be just replaced by log p over mu, and of course rho is replaced by this value. Times, so this is the measure, and 2 times 1 minus gamma bar p prime d p prime, yes, sorry, p prime and lambda. So this is a solution one can have by using this analogy. So there's no. So where, of course, one can use the initial value here So the initial condition is that the d log p over mu of lambda bar of p at the lambda is better at the lambda bar, where the lambda bar at the mu is equal to lambda. Okay, so this is the initial condition one can impose. So this lambda bar, sorry, here lambda bar solves this condition. Here x bar solves this condition. Solves condition. The functions that solve this condition. Okay, so that's the the solution of this equation. And then, so one can just use this equation, this solution as follows. So, suppose so this scalar theory with the master scalar theory has a better function such that it has the following behavior. So, as I mentioned, 5-fold theory has the beta function is positive, and I suppose there is some the higher reading, higher quantum correction bent this lambda, the function into a beta function like this way. And this is, as I mentioned last time, this beta of lambda star is equal to 0 is called the UV fixed point. Okay. UV fixed point. And then, so around here, one can just consider, so you can just linearly approximate the behavior around the UV fixed point. So the beta of lambda around the UV fixed point is of course some b lambda minus lambda star, and where b is positive. So this is capital B, not beta function. B is positive. So now for the slope, here is negative. Okay, minus b is negative. So, and just as we know that the derivative of lambda with respect to whatever p or mu will give a better function. So depending on how the convention. So therefore, so one can just write down so this equation as follows: so d log p lambda bar. So the beta function, just plug that one into here. You get so this is around, so approximately around UV fixed point. Fixed point. So this is around. You can just linearly approximate lambda star of lambda bar, and then one can just solve this linear equation as follows. So lambda star. So this is the condition at mu. So when p is equal to mu, you get that lambda star. So that's the condition we want to impose. So that the some constant over mu over p to the b. Okay. So once you plug this solution into here, you get this. You can check this satisfied equation. And when when p equal to mu case, this is just oh my goodness. When p is equal to mu, this is equal to 1. So lambda star plus constant. Okay, so sorry. So when p equal to mu, we just impose some lambda star is plus constant. Sorry, that's what we want to impose. Okay. Yeah. So here, so the condition we just imposed lambda star is of p equal to mu is just lambda star plus some constant. And as you can easily see, so this is UV fixed point. So when p goes to infinity, so UV means the p goes to infinity. One can check that this part becomes 0, so that lambda star, lambda bar approaches the lambda star. Okay. So that's what the UV fixed point means. And now B is positive. And then, so you can just take a look at the this solution. Solution of the this Collins-Manzik equation by using analogy of this bacterial evolution equation, what the column I used, then one can just obtain this fact, the exponent b in the so I hope network is okay. So if the P, so if P is really large, whatever. If P is very big, is very or high energy at high energy. So P is very big. So this solution, this equation, essentially the dominance around this factor, so that G2 of P has the following form. So G of lambda star. So since the high energy lambda bar approaches lambda star, so we can just approximate this solution as follows: lambda star with exponential of minus log P over mu, and you just have 2 minus 1 minus gamma lambda star. So at the high energy at high energy, so the coupling constant just goes to the fixed point, and this integral is dominated at a really high energy part. So one can approximate the 2-point function as the following way. And this can be written in terms of follows. So this can be written as follows: C times 1 over P squared. So you just use the exponential log and take log, and it's just the exponent shaped, and which is 1 minus gamma minus star. Okay. So this is the some constant. C is some constant. Yeah, it depends on G. G lambda star. Okay. And as you can easily see, so it's a remarkable fact that if the beta and the gamma are 0, then as we see, the P is I over P squared for scalar theory. And these two really come from the mass dimension 2-point function. Okay. So it's a 2-point function. It's essentially phi. It's a Fourier transform of phi of x and a phi of 0. It's a Fourier transform of the Fourier transform. And the mass dimension phi in 4 dimension has a 1. So therefore the mass dimension 2-point function is the should have the mass dimension of after the transformation, Fourier transformation, you should get mass dimension minus 2. Yes. However, so if you look at the fixed point of the UV fixed point, there's a collection by this gamma. Okay. So therefore, G2, the mass dimension of the 2-point function has some correction by gamma. So therefore, it's the mass dimension of 2-point function becomes anomalous. That's why it's called anomalous dimension. Dimension. Okay. So therefore, in the so interaction theory, even at a fixed point, the scaling behavior two-form function is also gets modified. That's why it's called anomalous dimension of the scalar field. Okay, so that's how you obtain the anomalous dimension. Sorry, I told you wrong. This one over sorry. Mass dimension -2 really come from the Klein-Gordon equation. It's Klein-Gordon equation of 0 of x is equal to delta function of x, right? X of 4. And then G, so this has the, so if you take the Fourier transform mode, this is replaced by P square, okay, P square. And then there's I here. And then this is a P square, and if you take the, so G2 is essentially inverse of the P square. Therefore, you get the mass dimension -2. Okay, sorry. It's not coming from this this dimension of 5. Sorry. I'm sorry, I told you wrong. Okay. So that's how you get what's the meaning of anomalous dimension here. Any question? How does it work? If you are watching this live stream, just please reply to me. Is it okay? Okay. So I'm going to erase. Okay. Any question? So I'm going to talk about the non-abelian gauge theory from now. And last time, so we talked about so the abelian gauge theory, and we tried to introduce the algebra and the Lie group. Okay. Lie group and the algebra. Okay, and then last time, so we talked about the matrix value as matrix Lie algebra. Matrix Lie group, and its groups and its their Lie algebra. Especially we introduce general linear SL and also unitary SU and the orthogonal SO. Okay, that's what we introduced, and then here corresponding GL SL U SU SU and then SO. That's what we introduced last time, given definition. In particular, so Lie algebra is G is given by, in my lecture, the X in N of X, depending on R or C such that the E to E I P X is inside of E group G. for any t. Okay. For any t, and then so we just give the I just give a definition of this Lie algebra, but I just want to make one comment in mathematics. So to define the I would say in mathematics there's a more formal way to define the Lie algebra at the tangent space identity of the Lie group, but they also take a different notation. I mean, here in mathematics there's no I here, but in physics we often use I. We often use I, but in mathematics we omit this one. In math, in usual math convention, so there's no I. There's no I. So be careful when you try to check the definition of the Lie group and Lie algebra in mathematical literature. So there is a conventional difference. So one has to be careful. Okay. So yeah. So I think I should mention that so here. And last time, so we talked about the definition of the GLN RC and C SUN UN SUN SON, and this is essentially the same as the matrix of R and C. And this is essentially element of the Mn Rc such that trace of x is 0. Okay? And Un, we have the x is element of Mn C such that the x is 0. Okay. Sorry, not 0. Sorry. The dagger is equal to 0, and here you impose the same thing, and you just impose trace of x is equal to 0, and here we just have Mn of R. Such that x is equal to minus x transpose. Okay. I just want to give you the dimension of dimension of G is the or it's the same as dimension. Dimension of Lie algebra G. So this is the dimension as a vector space of this Lie algebra. Dimension of G as a vector space. So these are metrics. So therefore you can just consider as some vector space. In particular, so it depends on the ground field or R or C. So the dimension of G. Okay, so dimension of GL and R is of course n squared. Okay. It's n by n matrix. So essentially, okay, real dimensions. Okay, so here. Real dimension of the Lie algebra G as a vector space. as a real vector space. Of course, if you use C, you have a double, 2 times n squared, and D, SL, and R is, of course, you have to impose one more condition. Okay, so therefore you just get rid of 1 degree of freedom and square minus 1. And how about D of UN? So as a real vector space, here it's I think it's n square. So here it's I use C for the I use C for the ground field, so that x is equal to x diagonal means that essentially, so you can just decompose the matrix of diagonal part and off diagonal part. Okay, and the off diagonal element are related by x is equal to x diagonal. So therefore, off diagonal element has n minus 1 divided by 2, right? Okay. So this is the entry that has the off diagonal in the or lower triangle, strictly lower triangular element. But since it's C, so you have to multiply by 2 to count the real degree of freedom. Okay, and in particular, so when you impose x is equal to x diagonal, so diagonal element has to be real. Okay, therefore there's only n degrees of freedom. And that will give you n squared. Okay. So how about D as UN? So this is n squared minus 1 because I impose one condition here. Okay. And then D SO n is, as you can easily see, that the x is equal to minus x means that so you just impose some condition between the strict lower triangular and the strict upper triangular. So they are related by upper sign. Okay. So therefore only have n times n minus 2 entry, and of course off diagonal n has to 0 because of this condition. Okay. So therefore dimension is n minus 1 over 2. And then so in this lecture I'm not going to talk about the symplectic as I mentioned last time. So symplectic I will give it to you an exercise. So these are the condition of the vector spaces. And here, and the last time, so I just introduced the Jacobi identity. So for x, y, and z in element G always is satisfied. Oh, sorry. The x, y, and z plus cyclic is equal to 0. Okay. So that's what we have seen last time. And often people just introduce the following basis. So it's a matrix, and as a vector space, one can just introduce so-called bases. So given a Lie algebra G, German G or G, people just write the element x such that the sum of a is equal to 1, dg, such that the xa, ta, capital Ta, where the xa is some element, it's just number, and Ta is, so Ta is, this is the basis of G as a vector space. And for instance, one can take And we often in physics literature we just take the following notation: 1/2 delta AB. One can always take the trace of the two elements in basis. Take a trace of two element basis, you give you delta AB up to some one half. Okay? So one can always take the basis such that this condition is satisfied. For instance, the example is as many of you know that let's consider SU2. So SU2, so we can just look at here. So it's the 2x2 matrix with a complex number, and taking trace is 0. So the T of A can be, so the dimension is of course 2 squared minus 1 is equal to 3. So therefore, dim of SU2 is 3, and then one can just take the basis as a sigma A over 2, where the sigma is the Pauli matrix. So the Pauli matrix, as you know, 0 minus I 0 1 minus 1. So this, of course, satisfies this condition. Is it plus? Is it okay? I already forgot the notation. Is it plus or minus? I already forgot. Anyway, so one can just take this basis and then you just plug that one into here. You can see, that you plug this one into here. So you can check this basis satisfies this condition. Okay, so SU2 is Lie algebra essentially the computation relation parametric satisfied. Okay, so far so good. And then so I can just rewrite the Jacobi identity in terms of basis. Then so the Jacobi identity in terms of basis can be just write down T A T P T C is essentially the same. I mean, is equal to 0, so you just do the cyclic way. Okay, so this is equal to 0. So that's the Jacobi identity in terms of basis. Okay. Furthermore, so as we know that so the computation relation. So the bracket so one can just Lie algebra endowed with this bracket structure. So bracket creates like a multiplication, as I mentioned last time, G. And in fact, so I can just write down this computation relation as follows. So in physics literature, people just often write down like this PC, TC. Where here the summation C is assumed. Okay, summation over indices C is assumed. So that is Einstein convention used. And in particular, so it's even if you take the computation relation, it's an element of G. So therefore, it can be written in terms of some linear computation of T, okay, T of C. And here, the coefficient is called structure constant. Constant. So this, yeah. So this, sometimes there is no I here and so on in math literature and so on. So you have to be careful convention. For really algebra like SO2, maybe complex matrix. SO. Okay. Okay, I received one comment from. So what's the definition of SON? So SON is the exponential. So this is x of n and r, such that the x transpose x is equal to 1, xt, and the determinant. Okay. And here we take e to the itx. Okay. Oh, I see what you mean. So here, this literally means 1 plus itx plus 1 half itx squared and so on. Okay. But to be a real element, of course, t is equal to r. Okay. In order to be a real element, so the generator of the matrix X should take the, let me think, should take the purely imaginary one. The element should be, let me think. Yeah, it should take the purely imaginary. Here, the generator of the SO should take the pure imaginary. The entry of X should take the pure imaginary one. Otherwise, this condition is no longer satisfied. Yeah. So thanks for the asking. For instance, let's think about the SO3 in that case. I think SO3 is the so let's think about SO3. SO3. So this is the matrix 0, 0, 0, and then here, if you take transpose, you get the minus. So therefore alpha, beta, and gamma, minus alpha, minus gamma, minus beta. So this is essentially the basis one can take. And then of course alpha and beta and gamma has to be purely imaginary. I times real number. Okay. Otherwise, so the element, if you take the e to the some power, you wouldn't get the real matrix. Okay. So that's why you have to be careful. Thanks for asking. So if you assume since this is pure imaginary, you can just take the just complex conjugate or maybe later. Okay, I hope. Thanks for asking. Any other questions? Okay, so, sorry, so I told you in that case wrong in this case. Okay, I understand what you mean. So this is not correct, sorry. Yeah, I think, let me think. Yeah, this is not correct. This is not correct. So in this case, it has to be I times R. Okay. It's a pure imaginary number. Sorry. Thanks for correction. Yeah. It's a pure I think oh my goodness, I told you wrong. Okay, I think I told you wrong. I think I'm very sorry. I think there should be plus sign. There should be plus sign. Let me think. Oh yeah. I think. Sorry. Oh yeah, this is correct. Sorry, this is correct. This is correct, but I think the entry has to be purely imaginary. Sorry, I think you're right. You're right. Entry has to be purely imaginary. Yeah, I think I'm correct. Thanks for correction. That's the SO has to be. It's a purely imaginary one. I times R. Okay. Yeah, so because of the I put I here, it should be I here. Okay. Thank you very much. Okay. Yeah. So let me erase. Okay. So where are we at? So we just introduced the structure constant here, so that the one can just rewrite the Jacobian identity here in terms of this structure constant. I mean it's very easy. F ADE F BCD plus F. Of course, you just everything becomes C. F is equal to 0. So one can just, since there are two computational relations, so therefore one can just rewriting this two Jacobian in terms of structure constant by just being secret about ABC. Okay. Then you get the Jacobian. I'm not gonna fill out, so you can just fill out by yourself. Okay, so that's the rewriting in terms of the structure constant of the Jacobian. And also, one can just from here, one can just consider so-called representation. Representation of Lie algebra. So representations of Lie algebra, I mean, it's a huge subject, and also it becomes one branch of mathematics. So I'm not going to go into detail, but I'm going to introduce the most important one. So representation of Lie algebra, if you have a G or K, acts on some vector space, some set. So this is vector space. As a matrix. For instance, the most the well-known one that as you know, so SU2, the algebra, is essentially the computational power matrix. Okay, so that so we know that it acts on J and M, right? Where the M runs from minus J to J. Okay? So we already know the SU2 J3 J plus minus. Everything can rewrite the Pauli matrix can be transformed into these. I mean J. I mean of course J3 over 2, and this is essentially x1 plus minus I sigma 2 over 2. Okay, and this is how to say, raising operator and lowering operator becomes raising and lowering operator for M, and J3 is they are eigenvectors of the J3. So this SU2 Lie algebra really acts on the space that is spanned by these vectors. Is called spin J representation. Spin J representation. And of course, as you can easily see, there's a 2J plus 1. So spin J representation, let's call P of J. P of J, and dimension of Pj is equal to 2J plus 1. Okay. 2J plus 1. Okay, 2J plus 1. So as a vector space, and one can just consider the similar thing in general Lie algebra, and I'm going to explain only like some particular important representation from them. Okay. So it's called, so one important thing is trivial representation. It's very, very boring one. So all the element, so dimension of B is one dimension. And all the elements TA is mapped to the identity. Okay. So the vector space is just one dimension, and all the generator of TA is mapped to identity. So it's just so boring representation. Okay. But more important one is fundamental representation. So fundamental representation, sometimes people will just call, some mathematicians call vector representation. But so the matrix TA is, as a Lie algebra, so the generator TA is mapped as it is, acts as a matrix as it is. For instance, as it is, TA act as on vector space as it is, or as matrix as it is. So for instance, SU2 case, we already know TA is equal to sigma A over 2, right? And then, so it's a 2 by 2 matrix. So it's essentially 1/2, 1, 1, 0, 0, and 1/2, I minus I, 0, 0, 1 minus 1, 0, 0, 1/2. Okay? So these are, and then the vector space is 2 dimensions. So the vector space B, dimension of G. So of dimension D. Oh, I'm sorry. It's not the same. Sorry. Dimension B here. Dimension B should be, in this case, dimension of B should be 2-dimensional. So essentially, so it acts, the matrix acts, so TA acts some alpha and beta, okay, as a matrix. So TA acts as a matrix. So essentially, this matrix acts as a matrix, like this way, and so on. So for instance, and then people just write down, people just sometimes write down F, bold F for, or like bold F for fundamental representation, but physicists often write down as the dimension of the vector space to represent the to express the representation. So for instance, SUN is, as I told you, X is an N of C such that X is equal to S squared, and also a trace of X is equal to 0. So as a matrix, it's n by n matrix. Okay. So the fundamental representation is the so the matrix n by n matrix and n by n matrix acts on n-dimensional vector. So alpha 1 to alpha n acts on, it will give you another vector. So beta 1 to beta n. Okay. So this is the action as a fundamental representation. So therefore, people just often write the fundamental representation is the bold n, and since the it's often hard to write the bold n in Blackboard, people just write down like somehow the how to say lower bar. Okay. Some people just write down like this way. Even SON, fundamental representation is the X is an n I r times and X is equal to minus X transpose. Therefore, so it's n by n matrix. Okay. So okay. So therefore, this fundamental representation often also write down n like this way. That's a fundamental representation. So you just TA acts like a really matrix. But another important representation is so-called. So in this case, it just spin one half representation. In this case, so SU2 case, it's just that alpha and beta. Alpha is spin up and beta is spin down, right? And spin down alpha. So 1, 0 is just a spin up, and then 0, 1 is spin down. Okay? So it's a spin 1/2 representation. The fundamental representation is the same as spin 1/2 representation in the case of SU2. Another important representation is just as I mentioned, the algebra G itself is can be understood. Interpreted as vector space, and then G can act on G by, for instance, if you have X and Y, you just take the quantity X, Y. So what I meant is that the So it's called adjoint representation. Okay, it's called adjoint representation. So given a Lie algebra G, so can acts G goes to G. Okay. So the vector space goes to vector space, the same vector space, so that if you pick by just acting on y is taken by x, y. Okay. So this is called adjoint representation. In particular, so the dimension of B, the B adjoint representation of dimension is essentially B adjoint is the same. The vector space is indeed Lie algebra. So therefore, dimension of G. Okay. So essentially, as a basis, TA, TB acts on I, F, A, B, C, TC. So therefore, another adjoint representation. So TB is a basis of G, and then G acts on the TB will give you another element of G. So therefore, representation TA, adjoint representation, is matrix which is I, F, A, and B, C. So sorry, I told you wrong. B, C, I, F, A, B, C. So what I meant is as follows. So the TA acts on some matrix, and then acts on matrix. In this case, the matrix size is dg times dg. Okay, and the vector represented here is alpha 1 alpha dg, and this represents essentially some Lie algebra element in Lie algebra such that the alpha 1, maybe I should use the lower indices, alpha 1 d of g, such that the alpha I t I, sum of I, is equal to 1 to dg, is the element of the Lie algebra. Let's call, say, shape y. Okay. And this matrix can be represented as FA. Okay, FA. Oh, sorry. R TA. And then this BC means the matrix element. So BC, matrix element, is specified this value, structure constant. Okay. So therefore, this adjoint representation is that the so Lie algebra acts on Lie algebra by bracket. That's called adjoint representation. Okay. I hope you understand what I meant here. In the case of the SU2 case, as you can easily imagine that the so this is a good exercise to do. So SU2 of dimension of SU2 is indeed dimension SU2. As a vector space D of SU2, so D of SU2, this is 3, as I mentioned, 2 square minus 1. And then SU2 is this representation of SU2 always is the one-to-one correspondence of spin J representation. And then we know that the spin J representation Bj dimension of speed j is 2j plus 1. Okay? And then, so representation, adjoint representation SU2 is the dimension of SU2 is 3 dimension. So therefore, the adjoint representation SU2 corresponds to when j equal to 1. Okay? So therefore, adjoint representation of SU2 is the same as in 1 representation. So in 1 representation. Okay. Any question? And in fact, so one can consider, as I mentioned, SU2 case, the labeled by half integer, right? So there are infinite many representation in general. So the representation, so TA is mapped to so-called under representation R. So bold R. So people just use bold R, such that the submatrix TAR, submatrix matrix BC. Okay? So and of course B and C runs are runs from dimensional representation, I think the people just write down dimensional representation like this way. D of R is the dimension of representation vectors as a vector space. So yes. So this is a matrix element. It's the matrix T of R. So R is some representation. Okay? In the case of fundamental representation, so TA. So this is small TA. I mean, it's a bit confusing. Small TA fundamental representation is the same as TA. Okay. But for adjoint and so on, adjoint representation, and then for T of A of trivial representation is always identity, a 1, just 1. Okay. Just 1. Okay. TA of adjoint representation is more complex. TA of adjoint representation is, as I mentioned, so it's written here. TA of F, as a matrix BC is equal to IF ABC. That's as a matrix. Yeah, BC element of TA adjoint matrix is this structure also, and so on. Okay, and then so important fact is that as follows. So it can be proven. So it's a huge literature of the representation of the algebra, and one can prove that the TA of representation is equal to some number that depends on representation times identity matrix. So this is just 1. So this is identity matrix. Identity matrix of the size D of R times D of R. Times D of R times D of R. So of course here I also assume the Einstein convention, sum over A. And this number is called quadratic Casimir. Okay. So it's a good exercise to do that. The for instance SU2 with fundamental representation of spin 1/2 is found. Okay. You can just check that the 1/2 1 minus 1. And then, so this is n square. 1/2 1 1 0 0 square plus 1/2 0 I minus I 0 square is equal to what? Let's see. So this will just give you 3 over 4 times identity. That's a simple check. So therefore, Casimir of the spin representation is just 3 over 4, like this. Okay. So this of course depends on representation R. Okay. So okay. And there's an important relation that the oh gosh, it's already this time. So important relation as follows. So one can introduce some notion. So trace. So as I mentioned at the so in the spin, it's just fundamental representation is let's see, trace of TA fundamental, TB fundamental is 1/2 delta AB. Okay, delta AB. So one can just take. Always in physics literature, we take the basis of the algebra in the following way. But if you look at the even representation, symmetrics under representation. Oh, I'm sorry, it's a B. Okay. Representation. So indeed, this is also satisfies some number times delta AB. One can just show that the all representation satisfy this convention. The under the trace behave like the orthogonal basis. Orthogonal basis, and then even under representation. And then the important relation is that the as follows: dimension of representation times times Casimir of representation, and then D of G is equal to C of representation. Oh, so this is representation. Okay, so that's the relation between Casimir and this C of R. Okay. This is the dimension of the so dimension of the Lie algebra Lie group. Okay. So let's check SU2 fundamental. So SU2 and R is fundamental, or it's the same thing, spin 1/2. Okay. So what's the dimension of fundamental SU2? It's just 2 by 2 matrix acts on 2 vectors. So the dimension D is 2, right? This is 2. And it's Casimir, as we mentioned, seen 3 over 4. Okay? And this is left hand side. And right hand side is D of G is what? As I already guessed, is 3. And then C of R is just written here, it's 1/2. Okay? Therefore, you can see the identity between them. And it's a good exercise so that to check this one in the SU3 case and so on is in the homework. So, any questions so far? Okay, I think it's a good time to take a break. So, let's take a break. If you have a question, just send me a message via WeChat. Oops. Okay, I think it's... Okay, let's start. So I received one question. I hope my answer is sufficient. If not, you can ask me later. Okay, so with this preparation, one can just consider nonlinear gate theory. So essentially, now so now we just so young else or nonlinear gate theory. Okay. So here we assume that the gauge transformation. So we just consider the for instance the last time. So we just consider the electron the Dirac field as the transform the gauge transformation like this way. But now here we assume the U. The last time the Abelian gauge is e to the I alpha of x, something like this. This is U1. But now minus. Now also U of x takes the Lie group so alpha exponential Ig sum of alpha a of x and ta. So that's the essentially. So the last time, so we just consider minus I alpha of x, and here is electron electron charge is negative values. That's why there's a minus sign. But Pascal showed that if you change the notation. Now here G is some positive value. That's I think what I would imagine. So that there's no minus sign here. So that when you go from G to E, you have to be careful. G is not coupling constant. This is the coupling constant. Link constant of Yang-Mills theory. So which is assumed to be positive. And now, so U is inside the element of the gauge group G. So here we just consider the gauge group. Group is G is Lie algebra. So sorry, Lie group. So this is Lie group. G is a Lie group, arbitrary Lie group. Essentially, Lie group I just introduced at this U, SU, SO, and so on. Then mu of x takes the following mu of A of x PA. Now takes the value of the Lie algebra. So this is Lie group. So gauge transformation. U takes a Lie group value, but gauge field takes a Lie algebra. Okay. And then as you can see, so last time, so when you just take the covariant derivative, so when you take covariant derivative, we just take a limit. Maybe I should write down here. So covariant derivative. So the mu of psi is just a limit of equals to 0, 1 over epsilon, take psi of x plus NE minus u of x plus NE, and x such that the psi of x. Okay. Oh, not u, sorry, c. Some Wilson loop. We introduce Wilson loop, where the c of y of x is exponential of the gamma of ds dx ds mu. I think as far as I remember, I put some IE right here. I think this is minus IE. Minus IE, where the gamma is some gamma is a path from, it depends on, yeah, I think a C of gamma depends on gamma x to y. Okay, and if the x, I mean this path is short enough. I mean it's short enough. I mean you can just x plus and e. So it's just a delta. And then if, I mean, so therefore if it is very short enough and E, x is equal to 1 minus I E A mu and mu and times epsilon and plus order epsilon squared. So now here we need to generalize it to the non-abelian gauge group. So that this one is indeed generalized as follows. So this is easy to generalize. So this is just a 1 plus IG. So the sign is flipped because the E to G. So that's mu A PA and mu epsilon plus order epsilon squared. The black back into here, and then I have to mention that the here psi takes the fundamental representation. So therefore, so as I mentioned, so this is matrix value. Okay, this is matrix value, and so therefore this has to be some representation of Lie group or Lie algebra. Okay, psi. And here it's just a fundamental representation. It's TA is just a, as I mentioned, so capital TA is a representation of fundamental representation dimension, small TA fund. So now for this, its Dirac field is now takes the following form: phi1 the phi dimension of fundamental of x, 1 of x. Okay. So it's now the vector value. Okay. So dimension fundamental. Okay. So here also we assume so from here, so it's no longer just ordinary Dirac field, it's a vector value of Dirac field. And C is also takes a matrix value. And then, as you can easily imagine that if you take the limit, what you will get is d mu of psi is indeed, so just plug that onto here and use this vector value Dirac field pressure mu psi plus I g. I think it is a minus sign. I think I have to be careful. Yeah. The minus sign A T A, and that acts on psi. So this is now matrix of fundamental representation, and psi is a vector, and this is also vector. So this is the covariant derivative one can take. Yes. And then, so here you have to be a bit more careful. So this is infinitesimal expansion for the Wilson loop, so that you don't need to care about so much about it. I mean, just only there's a x and x plus and e. There's some that we assume this is only like the shortest path that connect the just neighborhood point. But if you look at it globally, it really depends on gamma, as I mentioned last time. So if you take the different paths, gamma 1 and gamma 2, so the difference between the Wilson loop is given by curvature or field strength, as I mentioned last time. So it really depends on the path. And here, we assume that you just take the small division, okay? So this integral is just sum of a small division, right? As sum of, so this can be understood as something like sum of I exponential sum of I AI mu xi and then delta x. So that's essentially the meaning of the this integral. So if you take the delta x mu takes a really small limit, you have to be careful. So then this is essentially the product of I is equal to I, such that the exponential minus IE mu xi delta x mu. Okay. So this is product essentially. So you just take the Wilson loop, okay? Wilson loop in each segment. So Wilson loop in each segment, so that you just multiply them together, and you get the Wilson loop. But when you go to the non-abelian case, okay, you have to be careful. So let's do the step by step. Here, A mu is replaced by ATA delta x mu, okay? And then this is plus sign and g. Okay, so this is xi, x1, x2, x3, and so on, and you just take. x3, and then you just take product. But you have to be careful. Here, now it's matrix value. Okay? So if you, as you know, the matrix value A times B is normally equal to B times A. Okay? It's not longer true for if A and B are matrix value. So you have to be careful this product. Okay? So this product has to, so this, when you take the product, when you say product, you have to be careful about how you multiply them together, okay? So how you multiply them together, so that you have to take a product in path order way, okay? So therefore, when you take the sum, you have to take the sum over the path order way. So this ATA, delta x mu I times g, but when you take the sum over I, is you have to take the, so this I is path order, so the product is path order. So this I, taking sum over I is also path order. So if this is just a, there's U1 case, there's no TA, it's just a number, a complex number, the U1 case, they commute, so you don't need to worry about the order of multiplication. But here, it's matrix value, so that you have to be careful about the order of multiplication. So you have to do the multiplication by path order way. And here, often you have to do the P, the integral, path order summation becomes P times IM, and the exponential. So path order integral, you have to take a path order integral. Okay, so that's the, you have to be careful about the Wilson loop. And then, again, so F mu, the field strength is again, we just take the some number d mu, take a commutator of the covariant derivative to get the field strength. In this case, you have to take minus 1 over Ig in front. Then what you will get is just I mean here, yeah, of course, people just write down f mu psi minus Ig and mu psi. But now here, a mu is matrix value and the psi is vector value. Okay. And then here, so f mu and mu and mu. And as I mentioned last time, the cost of the matrix value for a mu is just a commutator of this one. And I think I have to put the minus sign here. Okay. Minus. So this is field strength. Now the a mu takes the matrix value. Okay. In particular, if you write down, so the matrix value, so that the f mu can be written as follows: f mu, it's a Lie, so or more precisely, Lie algebra value. So the this f mu ta. So that just one can write down the in terms of basis, then the f mu. Plus G F A B C A B mu C. So in terms of the basis of Lie algebra, if you expand it, in terms of basis of Lie algebra, th component is just written down like this, and when f, I'm sorry. I think yeah, I think. Wait a moment. Yeah, I think it's okay. Yeah. So this is so this commutator TD and TC will give you FABC TA. So this is the field strength or field strength. Okay, and then we need to be careful about the gauge transformation. So the gauge transformation now also the Lie group value, so that you have to be careful how the gauge field mu and also F mu is transformed under this gauge transformation. Where should I erase? Let me erase here. So this is gauge transformation U. So under the gauge transformation, as I mentioned last time, so the last time, so we just introduced gauge transformation as follows. So so as I mentioned, so the C of so gauge transformation C x plus E n is transforms as follows U of x inverse. Okay, and we have to do the same thing by just replacing C of x here. The Wilson line, infinitesimal Wilson line is by this matrix value. Of course, this one means the identity of the identity in the group. Yes, identity Lie group. So from here and take the epsilon goes to 1, epsilon goes to 0 limit will give you that the so C of x under the gauge transformation is mapped to this one. So from here, when you take the epsilon goes to 0 limit, what we observe is that this one is mapped to U of x and U inverse of x minus I over G partial mu of U of x U of x. Okay, and then so that's what we have done, computed by just taking epsilon goes to 0 limit. And here abelian case they commute, so that you just count the U and U inverse. But if the non-abelian case, they are Lie group and Lie group, and this is the algebra value, so that they no longer commute. Okay, this is how they transform under the gauge transformation. So the gauge field transform under the gauge transformation. And if you substitute this one into here, so one can just write down this transformation as follows. So if you substitute this one into here, the gauge transformation mu of x is transformed as mu of x, and then so this part, so if you just substitute in here, this one, so indeed this is adjoint representation, indeed, minus sum over A alpha A of x TA of AX x. So this part will give you these two terms when alpha is very small. Alpha is very small. Okay. When. And also the last time will give you as follows: minus plus IG plus IG sum over. Oh, sorry. The plus question mark. Okay, so that's what you will obtain from this transformation. Yeah. So as you can easily see, so this IG cancels this 1 over G here, and then I times minus I cancel with plus sign, you get the partial mu acts on just alpha, and then and TA is bring down, and then after that you inverse, and you cancel. And so therefore the second term will give you this one, and the first term will give you this one. And here we assume the alpha is very small. Okay. So the subleading correction for alpha square and so on inside this exponential is indeed it is ignored. Okay. Okay. So. Okay, so let's see how the gauge transformation, and then also we can just rewrite this one is as follows. As you know, gauge transformation. Oh my goodness, did I make a mistake? Yeah. Oh, okay. So the I think I'm correct. Did I make a mistake? I think I'm doing correct thing, right? Yeah. So, okay. So here we can just assume that this A mu is equal to plus d mu of alpha. Okay. D mu of alpha A, and then alpha of x A P. So we can just write down this covariant derivative is just a mu plus, you just combine them together in such a way that the d mu acts on covariant. So you can just have the just partial derivative, and this one can be understood as this covariant derivative. But this d mu has to be careful. This is acts on under the adjoint representation. Okay. So this is the commutator. I correct or not? Yes, I think I'm correct. Oh, sorry. I think what I'm writing. Sorry. Yeah, I think I'm sorry. Sorry. I think I should write like this way. Am I doing correct thing? Yeah, I think. Okay, sorry. So this is not correct. Sorry. So this is how the gauge transformation, gauge field and the transform of the transformation, gauge transformation, and if you just write down in terms of the basis of expand the basis in terms of TA and so on. So this A mu of C is transformed of this mu. Yeah. Oh, I'm sorry. I think what I'm writing is correct. What I'm doing, sorry. So this can be understood as A mu plus, so what I have written is correct, acts on alpha A TA under the adjoint representation. So partial mu, covariant d mu can be written like this way, right? Covariant derivative is just a d mu is equal to partial mu minus IG A mu TA. Okay? And then if you swap the order of the covariant derivative, this bracket, you get a minus sign. So therefore, you can just combine partial mu minus IG A mu acts on alpha ATA by adjoint representation. Okay, by adjoint representation. That's how one can just rewrite this this gauge transformation, and then so we understand how this gauge field is transformed under gauge transformation, and this F mu is how they transform is as follows. Yeah. Okay. So that I mentioned last time, so the so here now d mu of psi is transformed u of x d mu of psi, right? So that's how you construct the covariant derivative under gauge transformation. Under gauge transformation. Gauge transformation. Okay. Gauge transformation. So therefore from here, what we can just mention that the d mu and d mu is transformed under u d mu u inverse u psi. So therefore, acts on psi is transformed. So therefore, if you compare with this part, and you can just compare this part, and then psi is transformed on the gauge transformation u psi. Okay. So therefore, F mu is easy. You can just write down is transformed on the gauge transformation u F mu of u inverse. Okay. That's how it transforms. And if this is a Boolean case, they just commute, so the u and u inverse cancel. But if now F mu is the algebra value, and u inverse takes the Lie group value. Okay, so therefore they no longer commute. Okay, so that's how the field strengths transform under gauge transformation. Then one can just write down. Let's see. Okay, so the last, I just mentioned one thing. So exponential, if you consider the closed loop, gamma, so then so Ig pass order integral of gamma ds dx mu ds and mu. So, okay. So this one is indeed by Stokes theorem, is indeed, so you can just write down exponential RG sigma d sigma mu, this measure f mu. And this is an inside element of B group G by Stokes theorem. So this is the non-Hebbian version of the Stokes theorem. Okay. So this is the non-Hebbian version. So this P is really path order integral. Okay. You have to go you have to do the integral by path order way. Okay. So as I mentioned last time, so there is a to construct this theory, Yamil used the mathematics, so-called theory of fiber bundle, vector bundle. And then I'm not going to explain that one, but it's really illuminating to learn geometry behind. Essentially, you have a base and a fiber bundle. Gauge transformation is just transform u of x. This fiber is mapped from one point to the other point. And then the Wilson loop is indeed give you so-called parallel transform and so on. Parallel transform under the connection and so on. But those I'm not going to explain. But maybe UUA will tell you how to do that. So this is non-linear version of the Stokes theorem. Okay, and moreover, so since we just have defined f mu by just the bracket, so one can just mention that the so that you can just use okay, so this is Jacobi identity. Will give you that the new f mu rho and so on, and the cyclic in indices will be 0. So this is Jacobi identity. Of few strings f mu. A few strings f mu. Okay, so let's see. Thing. And then, so one can just introduce the action of Yang-Mills. So L is given by now on of trace of. So by taking trace, so the F is transformed under like this, right? So it's no longer invariant Lagrange transformation, but F mu U inverse U trace is the same as this one, because another trace you can bring it to here and they cancel. So the trace of f mu is gauge invariant, and then plus some bar. It's the same thing now. So this is the Yang-Mills Lagrangian. So this is Yang-Mills Lagrangian. Or sometimes you just not gonna use psi. I mean, and this psi is often called quarks, as I'm going to explain later. Often, or sometimes this is called QCD Lagrangian. Anyway, Young is Lagrangian and so on. Okay, so this is gauging parameter. As I mentioned, psi bar is of course transformed psi bar U inverse. But even if d mu acts on psi, it doesn't change the way they transform on the gauge transformation. Okay? So like this way. So therefore, the second term in also is gauging point under the gauge transformation. Okay, so that's how it works. And as I mentioned, so this is the sometimes QCD Lagrangian, or maybe I shouldn't say QCD. The same form will appear in the electroweak theory, but so when Yamel found this construct this Lagrangian, Pauli asks that so of course there's some gauge field, also the corresponding gauge boson, massless gauge boson should appear, but in nature you cannot find such a massless gauge boson around that time. So the question is, what is the physics behind? That's what Pauli asked Lee. Yang. But Yang couldn't answer, but the answer will be given later by lots of people, many people. So for electroweak theory, we need a Higgs mechanics to give the mass of the gauge bosons, and also in the QCD case or strong forces, of course, the gauge boson, which is called gluon, becomes massless in high energy, but in low energy, around that time you can only measure so-called glue ball. And due to the so-called strong coupling effect, it behaves like it looks like it has mass, glue ball. So it becomes strongly coupling or something. The analysis is very difficult. But if you go to the high energy level, the glue ball behaves not massless also. But you can around that time you cannot reach the high energy where the QCD behave like the weakly coupling. So that's called asymptotic freedom, which I'm going to introduce next lecture. So this is Young's Lagrangian, and we want to quantize it. Okay? That's the next goal. Any questions? Okay. So quantization which Yang is done by Faraday-Popov. Okay, so quantization by path integral. Quantization. So this was first done by the Faraday-Popov by using so-called ghost, which is via path integral. And I already explained the quantization, the electromagnetic Lagrangian via path integral. So we will follow the method. So first, as I mentioned last time, so the Lagrangian path integral Z. So I already have 20 minutes. So I have to be clever. Is given by, so this, let's go dA means dA e to the I S mLs is d4x d mLs. So that's what we're going to do, but you have to be careful. The connection divided by gauge transformation. And as I mentioned, so there's a space of it's schematic. The space of connection. There is the same configuration by gauge transform G, given the gauge field A. So you have to take the orthogonal slice, which is A over G. Okay, and that's the schematic diagram. So the gauge transformation, by gauge transformation now, so the A is transformed like, as I mentioned, U inverse plus partial U inverse, and then you have to put that proper IG, right? IG minus. That's how it transforms on the gauge transformation. So the infinite many, the same configuration, but you have to model that. To do that, so we introduce so-called the one. Again, it's the same thing. As a one is equal to d alpha delta G of A. Now gauge field has a mu like this way, and then determinant delta G of A. Oh, sorry, alpha. This is G of alpha of mu. So that's what we have done in the G alpha. So you just put this one inside the path integral, okay, where the mu alpha G is indeed the partial mu and mu. So yeah, so where did I put minus d mu and alpha. Okay, so that's so now the gauge transformation under so the infinitesimal. So when u is e to the I alpha of x, alpha of x, when of course alpha is takes the value of alpha a of x to a. There's summation over all the so alpha of x now the algebra value. Then under the gauge transformation, we already know that the A mu is transformed like this way. Isn't it plus or something? I forgot. Plus. Okay. So that's the gauge fixing term. Okay. So yeah. So the G of x, G. So we just take the Lorentz gauge A mu minus omega. So this is G. G of A is this one. So therefore, I just put the omega here. So that when we do the quantization electromagnetic field via path integral, we just impose the so-called Lorentz gauge with some function omega. Okay, omega, and under the gauge transformation. A mu is transformed like this way, okay, where the alpha is this one. So therefore, G of A mu alpha is like this way. Okay. So then, taking determinant, what you get is that the from here. So this is the omega is some function. This will give you as that the is equal to the alpha dot g alpha determinant of pressure mean pressure mean okay, so determinant pressure mean. So if you take the function derivative in terms of alpha, what's left is partial mu and d mu. Okay, d mu, partial mu and d mu. This is covariant derivative, and this one is called Fourier determinant. Okay, and what we are going to do is just insert this one into the path integral, and then just again introduce so-called the constant, the Gaussian integral over omega square, and integrate over omega. Okay, that's what we are going to do. Then what you will get is as follows. Again, so what we are going to do is the action of z of Yang-Mills is some number times dA, some number times dA, and it's just insert this one is d alpha. D alpha. Just plug that one into here. Delta G mu alpha, and the determinant of partial mu, and then d mu, and e to the I s m. And then again, so as we did last time, and you just insert some number, and then exponential of the omega, this will give you that as follows. So the dA, the delta function, and including this Gaussian integral omega, will give you the determinant of partial mu, d mu. It's the same procedure as we did last time in the electromagnetic field. Is that the e to the minus e to the I s Yang-Mills, but s Yang-Mills, but you insert something like a minus I over 2c partial mu and mu and then of course dx d minus I dx. So that's the effect of the Gaussian integral omega will give you this quadratic term of this Lorentz gauge. Now, of course, mu takes the matrix value. So that in fact, you have to take the summation over A. Okay. Summation over A. Summation over A. So that's what we are going to do. But what's left is this determinant. Okay. What's left is this determinant. So now we are going to use the following trick. So we are going to introduce, where should I erase? So if you don't know how to introduce the product term, so you can just look it back the first lecture of the video. It's the same procedure. I'm going to omit because due to time limit. So what I'm going to do is as follows. So just recall that we just have complex Grassmann variable Setter and Setter star. Then dn of Setter star and d Setter with I runs for 1 and then so e to the Setter I star and ij Setter j will give you determinant of n. So that's what we have learned last in the first lecture in quantization of the Dirac field and be a path integral. So therefore, what we want is just to interpret this determinant by some functional integral over complex Riemannian, and then whose kind of the action is just sandwich the Grassmann variable. Sandwich this Fourier-Popov operator by some complex Grassmann variable. So that's what we want. So therefore, what we want is determinant of partial mu d mu. Okay, partial mu d mu is some functional integral at a complex field, complex Grassmann variable field. Such that the e to the I d for x c bar and then partial mu d mu and this. So we just rewrite this Fourier-Popov determinant in terms of some complex Grassmann valued fields C and C bar. Okay. Of course, now d mu is again d mu is partial mu minus ig a mu, okay. And a mu is matrix value. And here C is indeed take the of course I just assume adjoint action. So C is now the algebra value. So C is CA of X and TA. And C bar is takes C bar of A and TA. Okay. So that's what we assume. And d mu acts by commutator. Okay. D mu acts by commutator. So that's what we're going to assume. And here C and C bar is some put by hand to interpret the determinant, this Fourier-Popov determinant in terms of some complex value, Grassmannian or the Grassmann field with this action. So therefore, it's put by hand. And we call this C bar is C is called Fourier-Popov ghost. It's not physical field, so therefore it's people call it ghost. C bar is called anti-ghost, and C is called just ghost. Okay, so that's. What we going to interpret how you interpret this Fourier-Popov determinant. So last time, so that without so in one case, this is just a determinant of partial square, right? Partial square, which is independent of A, so that you can just plug that out. So for Abelian case, you just determine partial square. It's just number. It's independent of A. Okay, so you can just get rid of so this bring outside the integral. But now d mu depends on A, so you can just bring out of the integral. So therefore, so you know treat this quadripolar determinant. We introduce so-called ghost field, okay, and whose action is like this way. So at the end of the day, what we are going to obtain is as follows. So Z is partial dA, partial dC bar, sorry, dC bar, dC e to the I S depends on A psi C bar, such that this S is given by d4x minus half trace mu and psi bar plus minus dash sorry minus there's a gauge fixing term here. So this term is coming from the Gaussian integral omega A. And then you have to add this term. And plus the ghost term. C bar minus partial mu. Oh, sorry. I think there must be minus signs missing here. Everything is. Yeah, I think everything missing minus sign here. Sorry, minus sign and minus sign and minus sign here. Minus partial mu. D mu C acts on C. C bar and minus. And okay, so this is the after the gauge fixing. So this is after gauge fixing. So this will fix the gauge, and the cost of the gauge fixing is these two terms. Gauge 2. Okay, so then we can just read off so-called the final rule for this gauge fixing Yam's Lagrangian. And before that, I just want to introduce so-called from here. So then, so we can just rewrite this action is as follows. So this action can be written as follows: d4x. So from here you can just you can read off the so-called the final rule for gauge fixing Yam's Lagrangian by using gauss and then the gluon or gauge field, and then also the torsion or the Dirac field. But before that, I just want to rewrite this action as follows. So this d4x, and in fact, as I mentioned, trace of TA and TB is equal to 1/2 delta AB. So therefore, this can be written as follows: minus 1/4 FA mu FA mu. Okay. So 1/2 will give 1/4. And then psi bar I is slash minus m psi. And then, so this term can just rewrite as follows. Plus, you just write down some speculative field, pressure A mu A plus. So you just click to be a plus C, minus C pressure mu times. Oh, sorry. I think. Oh, sorry. Here still, I mean this matrix value. Okay, so it's Lie algebra, and this acts on Lie algebra means it's still Lie algebra, and one has to take a trace. I'm very sorry. I missed trace factor. Trace, and the cost is actually you have to put a 2 here. So therefore, you have to put here a trace of this one and minus 2. And then if you apply this rule, like as we did here, so what you get is dA and acts on this one with a okay. So 1/2 cancel with this 2 here. So I missed trace here, sorry. So it's Lie algebra value, and this is Lie algebra value, so you need trace. Okay. Okay, that's okay. So I mean, physicists often want to write everything in terms of the indices. So this is the what's written in the Pascal ladder. Okay, that's how we obtain the rewrite the Yam's gauge fixed Yam's Lagrangian. And as you can see, once you perform the Gaussian integral for B field, okay. So here now I assume SA, B, C, and C bar and psi. Psi I did write A psi C and C bar. And C and C bar is this one. And then, so this is equal to dA, dB, okay, sorry, deep psi bar. Then, or maybe the other one. Times e to the I S A B psi bar and C bar. Okay. So after performing Gaussian integral so B integral, you get this one. And here, so this action has a really nice property that it has a BRC transformation. so-called BRST transformation, which is the, I'm not going to write down what the BR transformation is, and which is the exercise of the in the homework, the last three, problem 3. So this BRST stands for, I think this is the Italian, road, and then the last person is, I think, the Russian, and then QT. The abbreviation of these four guys, BRC transformation. It has a so-called invariant BR transformation. So this action is invariant BRC transformation. You have to check by yourself in the homework problem 3. Okay, I think it's almost time, so I will stop here. Any question? So I will wait for a few minutes. So if you have a question, just send me a message via WeChat. Otherwise, I will finish. Yeah, just send me a message if you have a question. How was the network? Was it okay? Oh yeah, why do we? It's again. So the purpose is to see BRC transformation explicit. So you can see the it's called if you so there's some so-called the boson becomes some fermion becomes boson. That's BRC transformation, which is written in homework problem 3. That the and also here so-called this action can be written as mu. So minus 1/4 f square. I mean just write down is some BRC transformation, some Lagrangian L tilde. So this Q is so-called BRC generator, and then so this the rest of the part. So this rest of the part can be written in so-called BRC exact form, and this Q square is equal to 0, so it behaves like a differential. It behaves like a differential form. Okay, and then the rest of the part can be written nicely in terms of Q acts on some L tilde. That's why we introduce B. By just the integral of the B field, you get this gauge fixing term. But by introducing B field, so the BRC invariant on the BRC transformation becomes visible. That's why that's the what the Popov did. So the rewriting is really just for the sake of the in order for this Lagrangian to be invariant under BRC transformation. That becomes manifest once you introduce B field. Any other questions? I mean, you can solve problem 3 so that you can understand why we introduce B field. That's why I stop here. So that you can solve the, you can understand you can solve the homework, and then you understand what it means BRC transformation. Any other questions? Okay, so it looks like there's no other question, but even if you find, so Friday 7:30 I will set up some Q&A session, so you can just, till then you start solving homework or whatever. Reading Pesky and Schroeder, even previous section is okay. Please send, so we'll have the Q&A session on Friday 7:30 at night. And we will use Zoom, and I will use iPad to answer the questions. So if you can find a question, just send me a message via WeChat or email, whatever, so that I can just prepare for answering to your question. If you can find it before then, I will appreciate it. But if you find some question while we are talking in Q&A session, that's also okay. But if you find some question beforehand, just send me. Then I can smoothly answer without switching with someone. so let's meet Friday if you're interested. And then, okay, thanks for watching. Bye bye.